Hello, welcome to this exploration of polymers, and in this particular lecture we will focus on the polymer applications in damping and what is meant by damping. So, our focus will remain on uses while we try to get an understanding about damping applications of polymer. And this will be done by first looking at energy dissipation, which is central to damping behavior. We will see that all damping materials will lead to energy dissipation, and especially energy dissipation with respect to energy storage capacity. So, it is the ratio of these two energies which gives us an idea about whether a material is damping material or it is not a good damping material. And we will end the lecture by looking at a simple model which is useful to describe the rubber response, and rubber are very good damping materials. So, through this lecture we hope to understand the damping behavior and application of rubbers in such damping applications. So, let us start by first thinking about energy dissipation. Since a lot of dynamic testing involves an oscillatory test, so we will consider energy dissipation during a cycle of test. So, as we have seen several times that what we do during a cyclic test is maybe apply let us say sinusoidal stress, or we could apply sinusoidal strain, and then we basically measure what happens to the strain as a function of time, and then we know that depending on the relative variations of stress and strain, we can get the loss modulus, storage modulus, or viscosity, which is eta prime and eta double prime. So, several in phase and out of phase quantities can be defined, which give an idea about energy dissipation and energy storage in the material. So, let us look at a case where we are applying, let us say, a sinusoidal strain input with an amplitude E0, and as we know, the stress will be therefore characterized by two material response functions, E prime, which is the storage modulus, and E double prime, which is the loss modulus. And we call these moduli so because one of them is out of phase with the input strain, and the other one which is in phase. So, in phase tells us about the elasticity in the material, and therefore E prime is storage modulus. And now the energy dissipation is based on the amount of stress that is being applied, that the material is subjected to, and the rate of change of strain. So, this you can think of in terms of basically the work being done, and work being done is force into distance, and the rate of work being done will be force into distance into time. So, basically what we have, instead of force into distance into time, we have stress into strain rate, and I leave it to you to do small units rationalization and see that when we talk about stress into strain rate, we are talking about energy per unit volume per unit time. So, basically we are saying power per unit volume. Remember, power is energy per unit time. So, basically what we have is energy dissipation per unit time per unit volume, and that is given by stress into strain rate. And given that we know both stress and strain for this sinusoidal variation in terms of response functions E prime and E double prime. So, just to highlight the fact that what we are writing here is for a general linear viscoelastic material, because only thing we have assumed so far is a stress of a form where frequency is omega, because input frequency is also omega. And so, we have assumed only linear viscoelasticity, otherwise it could be a material of any different kind, because we have not specified what is E prime and what is E double prime. So, in general then the overall power per unit volume is going to be given by basically some functions of sine and cos, and we could do this by in terms of per cycle what happens, because this is as a function of time. So, let us look at, because material is being subjected to several cycles, we will look at what happens during one cycle, and that can be done by just integrating this from 0 to 2 pi by omega, because one cycle is 2 pi by omega, omega is the frequency. And if you do that again with some algebra, you will be able to see that E prime in fact does not contribute to energy dissipation, and that should not be surprising to you at all, because E prime signifies elastic storage, and it's E double prime which signifies viscous or loss properties of the material, and therefore that contributes directly to the dissipation in the material. You could also look at the power itself or the energy, and they are related to each other through basically omega. And so what this says is E double prime is a very good determinant of what's the energy dissipation in the material quantitatively also, because we can look at what is the amount of energy dissipated in a cycle, and that gives us a capability of material to dissipate energy, and in turn we will see that that's what a damping material should do, it should dissipate energy. And so now let's look at the overall the dissipation rate for, let's say, Newtonian fluid. And Newtonian fluid is where G prime or E double prime, you could, so as I have mentioned, E is usually indicated whenever we do a tensile loading, and G is whenever we do shear loading. And so, but depending on what material is being tested in which mode, you can either have G double prime or E double prime. And so, for a Newtonian fluid, you can show that E prime, E double prime and G double prime are nothing but eta times omega. So, if you substitute it here, we get the expression for dissipation rate in Newtonian fluids. And since we know that E dot naught is nothing but omega times E naught, strain and strain rate are related to each other through omega. You can just take a derivative of this with respect to time, and omega will come out, and you will get basically this relationship. And so, what we get is the magnitude of amplitude in terms of E dot naught squared. So, this is nothing but stress into strain rate squared, and sorry, stress into strain rate, because eta into E dot is the stress and E naught is the strain rate. So, that is the amount of dissipating energy in a material. We could do the other side of it, which is the energy storage, and so the energy storage per unit volume is basically given by stress into strain. So, this is again the work being done, load into distance, but per unit volume, and therefore stress into strain, and strain, remember, is distance per unit distance. And so, again it is a functions of sine and cosine, and again if we do integration, we can show that the energy during one cycle is directly related to the storage modulus. And for a Hookean solid, since we know that storage modulus is a constant quantity, which is nothing but, let's say, the Young's modulus of the material, then energy involved in a cycle is just E times, and this is again stress into strain. So, that is going to be sigma into E, because the sigma itself is E times the modulus So, E times modulus into E. So, this is some measure of the storage energy during one cycle. And so, what is important for a damping material is to see the ratio between the loss and the storage. And generally, given the expressions that we have got, what we will get is this ratio of loss to storage is directly related to tan delta, which we have defined earlier, which is just the ratio of E double prime by E prime or G double prime by G prime for shear mode. And so, the tan delta is an important determinant, tan delta, which is a material property which tells us about the loss in the material, and we call it loss factor or loss tangent. It directly tells us about the ratio of energy loss to the ratio of energy storage by a material during a cycle. So, let us look at and consider what is the phenomena happening during damping of a material. So, damping is basically where we put the material, and let us say one side is vibrating, the other side should not feel it. So, for example, a machine which is located on a floor, we put vibration isolation pads below, so that when the machine vibrates, we on the floor should not feel the vibrations. The reverse could also be true, that if we have a very sensitive instrument and if we walk on the floor, our walking shouldn't induce vibration to the instrument. So, therefore, again we vibration isolate. So, what this vibration isolation device does is it takes the mechanical energy which is due to vibration on one side and absorbs it and does not transmit it. If you have a perfectly elastic material, then what happens is whatever vibration is being felt by this material will get transmitted to the other side and it will not dissipate any energy. So, generally if you look at displacement, a damping material would imply that displacement will die over time. So, whatever vibration are caused, if I let us say do the vibration at some instant of time, I apply some load and the material starts vibrating. If I leave it, then over time the energy of the vibrations will slowly decay to 0, and that is a characteristic of a damping system. So, displacement as a function of time will keep on decreasing. So, you can see that the amplitude of displacement keeps on going down and eventually of course it will go to 0. And so, the idea here is to say that how does this displacement vary as a function of time, and for a damping material of course this displacement has to go down with time, and that can be measured by estimating what is the logarithmic decrement. And this is basically a ratio of amplitudes in successive cycles. And so, amplitude in nth cycle, so let us say if this is nth cycle and this is n plus 1, then we take the ratio of these amplitudes, and it can be shown that that is directly related to the tan delta that we discussed just now. So, therefore, this logarithmic decrement is what is characterized for damping materials, and if we have let us say a system which is undamped, then delta is going to be 0, and for this case of course the displacement versus time will just look like this. So, that there is no change at all as a function of time, it is an undamped system. But whenever damping happens, the amplitude will go down, and rubbers and many of the amorphous polymers and wood have actually the damping factor, this logarithmic decrement, in the order of 0.01 to 1. So, it is a 2 orders of magnitude change, but if let us say you compare it with ceramic and metals, they have far lower logarithmic decrement, and clearly therefore ceramics and metals are not good damping materials, while many times rubber and in fact even wood can do a very good job of damping and vibration isolation. So, in the closing what we will do is look at a generic response of rubber materials, given that they are used so much in case of these damping applications and energy dissipation applications. So, viscoelastic response of rubber generically is follows. What we have is if we subject the material to low frequencies, since the material is in the rubbery state, segmental mobility is there, and segments can fluctuate. So, this is where segmental mobility is present. So, this particular data that qualitatively is being shown is at some temperature T. So, it is an isothermal experiment, but frequency is what is being varied. So, at low frequency, given that segments can move around, we get E prime is constant, and E double prime is lower than E prime, which means the material is more elastic, then it can dissipate energy, and this is where we use rubber bands or many of the other materials. So, where the loading is slow, and in this case therefore the material is predominantly elastic, and that is why we use elastic rubber band or many other rubbers, where we are exploiting the fact that when you deform and release, it comes back. Now, when you start subjecting the same rubber to higher and higher frequencies, what happens is now the frequencies of vibration and frequencies of mechanical loading are similar order of magnitude as the segments relaxation time and or the time scales associated with segmental relaxation. And so, what happens is the bond rotation and bond fluctuations and the segmental mobility, these start absorbing the energy, and lot of this starts happening, and there is a resonance phenomena, which is what we have alluded to in whether it is FTIR, molecular spectroscopy, dielectric loss, when it is electrical dielectric spectroscopy, or now this is mechanical spectroscopy. So, therefore, E double prime starts increasing as you increase the frequency. Of course, given that we are now increasing the frequency, it becomes more and more difficult for segments to also fluctuate and do their mobility, and so they also start storing more energy. So, E prime also increases. But beyond a certain frequency, again the dissipative losses go down, because now the segments have become almost frozen, and so again they lose the ability to dissipate energy, while ability to storage keeps on increasing. And so beyond a certain frequency, material becomes glassy. So in effect, in frequency, what we do is we are going from a rubber to glass transition. And since I said this, I am sure some of you can spot that I can do the same plot pretty much at a constant frequency, but as a function of temperature. Now, just think about whether if I plot this data which I am doing now as a function of temperature, will temperature be increasing this way, or will temperature be increasing this way? And this data, of course, same data can be thought of at some other constant frequency. So, I'll leave you to think about this, and based on our other discussion, you should be quickly able to answer this question. So, let us look at a simple model which can actually capture this, and it is called standard linear solid model. There is an electrical analog also of this model, and that is called Zener. So, sometimes when you search the resources, you might find Zener as another popular model, where the capacitance and resistances are combined in a way that you get this response, which is a good combination of elastic and viscous, and importantly it gives a more solid like response. If you recall my discussion related to Maxwell model, it is more applicable for fluid like response, and therefore creep cannot be explained. On the other hand, Voigt model, which was again a very simple model, could be used for creep, but it could not be used for stress relaxation. So, the standard linear model does a good job with both of them. When I say good job, it does a qualitatively reasonable job, that we can see that in creep actually material does not just keep on creeping like a fluid, it deforms and then stabilizes. The strain becomes constant after some time. Similarly, in stress relaxation, stress does not decay immediately, or stress does not remain constant like a Hookean solid, but it decays over time. And so, it is a 3-parameter model, and for those of you who are interested in the mechanical analog, you can look at and try to justify in terms of the spring and dashpot. This is how the standard linear solid model looks like. And I want you to think about which one of the spring is E1 and which one of spring is E2 and why. The eta is basically the damping response, which is the Newtonian like response or the viscous response. So, if you look at response of this particular model, and again how you get the response of the model is in this particular equation, you just substitute, let us say, a sinusoidal strain. So, let us say if you apply E naught equal to sin omega t, we are saying that we are subjecting the material to a sinusoidal strain. So, when you substitute this here, you will get an ODE in sigma, and then you can start with an initial condition that stress is a particular value in the beginning, and then just solve initial value problem and then get the solution. And based on the solution, again you will get a sine component and a cos component. When you split it in the two, you can get E prime and E double prime. And if you do such a calculation, also there are analytical expressions available. So, if you just do some search, you can find out the analytical expressions for E prime and E double prime for standard linear solid model. And if you plot those, you can see the qualitative features, that E prime is constant at low frequency, then E prime is again glassy state, higher modulus at high frequency, and then the G double prime or tan delta also will go through a peak. And so, this rubber like response is qualitatively described by a standard linear solid model, which is the simplest of a model which can give this rubber like response. So, the damping materials that we have talked about are rubbers, and whether it is natural rubber or whether it is styrene butadiene rubber, neoprene, or even other families of acrylics, for example, or urethanes and silicones are common examples of damping materials. And generally if damping has to be achieved, then we should minimize the secondary interactions and there should be no crystallinity. So, therefore, in general, if damping behavior gets affected, it decreases due to strong secondary interactions and presence of crystallinity. Can you think why this would be the case? Why would secondary interactions lead to less damping? And you can think also probably in terms of whether in wood, whether cellulose is going to contribute to damping or whether lignin is going to lead to damping. You can try reading about it. But what does secondary strong interactions imply in terms of segmental flexibility? Or crystallinity, of course, always implies loss of segmental mobility. So, that answer is probably a little more easy. So, just think about it and it should be a relatively easy answer in terms of trying to justify why should segmental mobility decrease with secondary interactions and therefore, it will lead to less damping. Now, look at the data for an example material. In this case, it is from a commercial literature of a 3M acrylic material. And the way the nomograph gives is basically for temperature and frequency and G prime and the loss factor. Because for damping applications, loss factor tells us about the energy dissipation capability. Quite often we will have this also material subjected to loads and it has to withstand load. So, therefore, E prime or storage modulus is also important. And so, these kind of data are given in this case G prime because again it is a shear based testing. And you can see that for a frequency, as frequency increases, the E prime G prime increases, or as temperature decreases, the E prime also increases. The tan delta on the other hand goes through a maximum and so that is again understandable because tan delta is related much more closely to segmental flexibility. Now, how these materials can be tested is we can make a sandwich structure of two different surfaces from which they are supposed to absorb the vibration. So, in this case, for example, a laminate is made which is stainless steel and polymer and stainless steel, and then it is subjected to vibration, and then you can try to look at what happens to loss factor of the laminate as a function of, let us say, temperature. And you can see that if you use 3 different types of acrylic materials, you get maximum in loss at different conditions. So, therefore, if you want to design a particular polymer for a given application, you can then look at this loss factor and see where is it maximum, which frequencies is it maximum, which temperature is it maximum, and then choose a material appropriately so that it maximizes the energy dissipation in the given frequency range and in the given temperature range of interest. So, with this we close this discussion related to damping behavior of polymers, mainly rubber materials. And now in coming lectures, we will look at some of the aspects related to superposition and some properties of blends and impact behavior of materials and so on. So, with this we close the lecture. Thank you. Goodbye.